AP. Second term. Now we need to start using this. So I'm going to run out of space if I start doing that Pn minus 1 notation. So I'm just going to kind of jump to what it, well, I'll write the generic notation. So it should be 5 times the term before it. So 10 minus 7 is 3. Third term, 5 times the term before it minus 7. 5 times 3 is 15 minus 7 is 8. Someone correct my arithmetic if I'm wrong. 5 times the term before it minus 7. 5 times 8 is 40. Minus 3 is 33. I think. And then the fifth term, oh Lord. 5 times 33 minus 7. What's 5 times 33? I don't know. Is that the final answer, or is that just the... So 165 minus 7 is 158. Okay. Y'all don't know how bad my arithmetic is, I swear to God. So we had, where are my terms? We had 2, 3, 8, 3, and 158. Questions, concerns on that one? All right, but I see some people scribbling, so hold on for like 5 seconds. And then the next one, we want to use those first 5 terms to guess a closed form. So remember, that's essentially that non-recursive function that should match. So what are our first 5 terms? Whoops, should change back to. The first term is -2. Second term would be -2 plus 6 is 4. 4 plus 6 is 10. I should have written these in a kind of different way, but I'm set this way anyway. 10 plus 6 is 16, and 16 plus 6 is 22.
I don't know if you usually do or not, but could you post this like under today's warm-up? Or
Sure.
yeah, I just want to have everyone review it.
If I write it in red, I'll see it before I close it. So notice that all of these terms are, of course, increasing by 6 because that was kind of the point of the recursion. So this turns into an arithmetic sequence, essentially. And remember, when it's arithmetic, that's going to give us a linear function. Side note, if it was the geometric, where each term is multiplied by something else, something to get the next term, that's what gave us our exponential function. Nudge, nudge, wink, wink. Remember, that looks like some original number times, I'm going to suggestively write r to the t. But so here we have a linear function, so we'll have some y equals m. Well, I guess I should use n's instead of other variables because those are the variables that we have in this situation here. So essentially, remember what we do here now is we essentially pull out whichever one of these terms makes us happiest. I'm going to just pick the first one. And so we're going to use that as essentially our point of this linear function to solve for that b value that we don't know. So the 1 is going to go in for n and the -2 is going to go in for y. And then that, common difference in this arithmetic sequence is going to be the slope. So we're going to have -2 equals 6 times 1 plus b. 6 times 1 is, of course, 6. So you subtract 6 from both sides to solve for b. -8 is b. So, well, I guess I should write. I'm keep switching notation here. F of n. What am I? Slope is 6n minus 8. So essentially, your common difference there becomes the slope. Take whichever pair of numbers you want. Solve for b. It shouldn't matter which pair of numbers you take. That's supposed to be the point. You should still get -8 no matter what.
Can you prove that and just show it on another one?
Sure. Watch it not work. Now I'm like terrified. Boom. Actually, I'm not done this question, am I? Because it would also, we also were asked to find the 20th term. Oh, I'm going to regret that. So we're going to take a guess at P of 20 because we should be able to say that that would be equivalent to F of 20. So 6 times 20 minus 8. So 120 minus 8 is 112. Ooh, give me a sticker for the day I did it. Whoops. Let me kind of get most of that in there. Questions, concerns on that one? Oh, there's a chat. Yes, I can. Another example of that second one, Madeline? Is that what you mean? Okay, sure, I can think of another one really quick. Someone wanted to look at this first example really quick though, so let me leave this up for a couple seconds. Yeah, Sam, so we were talking about oh my God, my brain. Oh, when we were talking about arithmetic sequences, we had that common difference, which was D, and yeah, in this case, our 6 would be that D value. All right, looks like you've done that one. So let's do, you want another one of these? Sure, why not? I want to make this shorter. Well, now I got to think of something off the top of my head. Let's do 1/2. 4. Sure. Pulling things off the top of my head is never a good idea, but we'll try it. Let's find the first 5 terms and try to figure out what's going on here if you don't already see what's going to happen. So we've got 1/2, then we take 4 times 1/2 is 2, and then 4 times 2 is 8. 8 times 4 is 32, and 32 times 8 is 256. Times 4. 32 times 4 is 128. Thank you. Yeah. But the non-math is the stuff I'm good at. The arithmetic. Anyway, so if we kind of notice what's happening between all of these, and with these ones, you can kind of see it from the beginning, maybe, once you get at these, they're all being multiplied by 4 to get to the next one. That's what the thing it tells us. So we're multiplying each one by 4. So we're essentially in a geometric sequence here, which is going to give us an exponential. So when we were talking about geometric sequences, we had a common ratio, which was that number that you were multiplying each term by. So then in that case, our ratio would be 4. And now this is, again, where we pick whichever one of those points makes us happiest. I actually might pick the second one this time because I don't want to work with a fraction. So I'm going to pick that second one. And since it's an exponential, it's going to look like some f of n equals some, I always use p naught for exponentials, but you know, you can make that whatever letter you want. So we'll have 2 equal, well, maybe I'm going to use a third one so that I'm not using 2 and 2, so you can see which one goes in the what spot. So 8 equals P naught, R was 4, and that N value is 3. Oh, I'm going to regret this. So 4 cubed is 64. I should probably be able to do that in my head, but I can't. And then 8 divided by 64, that's 1/8. So we would have to divide 64 by both sides, on both sides. That reduces to 1/8. If you were to write it as 0.125, that wouldn't be the end of the world. Which tells us that our closed form function is most likely 1/8 4 to the n. So we find either a common difference or a common ratio between our terms. If it's a common difference, it's arithmetic, so it's a linear function. If it's a common ratio, it's geometric, so it's an exponential. Put either one of those terms and your common whatever into the generic format of the equation, solve for the last value that you don't know, and then write the generic equation. What up?
You got Q because you used P3.
Yeah. I was gonna use, so I chose not to use P1 because I didn't want the fraction. And then I was like, oh, if I use P2, then they're all 2s and maybe people won't realize which spot they're supposed to go. So I used P3. But just like with the other one, it shouldn't matter which point you use. They should all give you 1/8 if you were to plug them in. Questions, concerns? I'm trying to leave the chat off, so wait, does it actually make it any smaller? Oh no, it doesn't, so I'm just gonna leave this up then. Where did you get the P naught function? You just know it. So the two types of functions we need to know here is that a linear function looks like some y equals mx plus b, and exponential looks like some, I usually write it as p naught a to the t. That's just the generic format of that type of equation. That's technically prereq material, I believe. So it's just know it. I don't really know what else to say besides that. But I got it because since it's a geometric sequence that we get, and we notice that the difference between the terms is that you're multiplying by something, that's exactly what an exponential function does. So there's like this relationship between a geometric function and an exponential equation. That exponential equation just came from, that's the form of an exponential equation. But maybe this is also your question. It comes into play specifically because we have this geometric sequence. And since a geometric sequence gets to its next term by multiplying by something, which is exactly what an exponential function does, we can use an exponential function to model a geometric sequence. Hopefully that made sense. Any more questions? Yeah. So once you find the common whatever ratio or difference, what you do then is you take your common ratio, in this case, that's going to be my R value, but I need to know what this P naught is. Well, I have F of N's and N's. Those are all my things over here. So I chose whichever one made me happiest. So I chose P3 equals 8. So that's why the 3 shows up. You could pick any one of those points you wanted. It would change it would change what this looks like, but it wouldn't change the P naught answer. Yes, so if you find that it's a geometric sequence, that would be that you're multiplying. So whenever you're multiplying each term by something to get to the next term, it's geometric. And whenever it's adding something to get to the next term, then it's always arithmetic, which means linear. Exactly. I don't know why it's not telling me who's saying that, but I guess it doesn't really matter. So yeah, that's exactly right. Anything else? All right. Since I'm doing our notes in OneNote now, I can just pop over there. Yay! So last time we talked about 3.2, and today we're talking about 3.2, part 2. I've told y'all that your exam's coming up, right? Next week. I'm almost done the review guide, so that should be up tomorrow on Blackboard. Anyway, we're gonna. I'll talk about that later. So, what we have to talk about today is something called induction. So on in this section, sorry, the first part of this section. So the thing we did on Tuesday, we were finding those closed form sequences, like we just did. But remember, we were essentially guessing at them because we didn't know, we didn't quite know yet whether they would work for absolutely all the terms. We assume that they probably will. Nudge, nudge, wink, wink, they do. But we didn't have a way to prove that yet, and that's what we're going to talk about here, is how to prove that those things actually follow the way that they should. So recall that a recurrence relation essentially has two parts. It has the base case. Woo, that's it. Has the base case. And that's the one that you're essentially just told is whatever. It's usually the n equals 1 piece. And then you have the recursive step, which is the thing that told you how to get to the next term. So to prove that these closed form solutions are equivalent to their recurrence relations, what we're going to use is we're going to use something called induction, which requires a kind of similar approach to a recursive relation. Is we're essentially going to start with the base case. We're going to verify the base case. So essentially we're going to show that the recurrence relation, oh, sorry, that shouldn't be an n. The recurrence relation at 1 matches the function at 1. Like, what's the base case, and show that it actually holds. What we're going to do then is we're going to assume something called the inductive hypothesis. And I'll kind of explain why this is what we do in a second. So you essentially assume that that recursive relation at some k minus 1 is equal to the function at k minus 1. You assume that to be true. For some k greater than 1, that's like a little thing you just always have to tack on there. And you're going to use that to show that they're equivalent for k. Why the heck does that work? Here's why. Well, kind of a generic, semi-wishy-washy idea of why it works. So essentially, think about it as if so think of induction like climbing a staircase. So let me there we go. I got it in there. So we got like this little staircase going on. So if you think about going upstairs, the first thing you have to do is actually step onto the staircase. And that's kind of the idea of verifying the base case, is you actually have to get on. But then to climb the stairs, you do the same exact thing for each stair. You just pick up your foot and put it on the next step, right? Same thing each and every step. So essentially, if we show for some arbitrary value k, how to get from the step below it to that step, if that makes sense. If we show it for any generic step, then it's that same process for every single step. So if we know a starting point, and then we can verify that we can make each step from that step, then you've shown them all. Does that make any sense? So this is why this step 2 above, and I mean this thing, the inductive step, I should have put the there. The inductive step, that says steep. The inductive step is enough to finish the proof. But that's also why you need those two pieces. You need the base case because if you haven't started anywhere, like, so with the inductive step, it's proving if I'm here, then I can get to the next step. Well, that's all good and great, but if you don't actually have a starting spot that you know is true, then that doesn't help you at all. So we need to show that one of these things is true and that we can also always get the step above it And once we've shown that one's true and we know how to take the step above it, we can now just stairway to heaven this thing and keep going as far as we want to. We don't have to keep going, but that's kind of how it works. Okay. So this is exactly what I just said. So remember, we've always got to do those two things. So let's see a couple examples of that. Well, there wasn't much to write. I'll leave it up for 5 more seconds. Just in case. Okay. So back in Tuesday day, we showed that this recurrence relation was, we guessed the closed form of 3n plus 2. We did. So now we're going to prove that that actually is the closed form for that recurrence relation. We're going to use induction. So step 1, base case. If I don't write a little smaller, I'm probably going to run out of space. So this is when we need to show, so just a reminder what base case means, is that when you use the first term, now it's just the first term, so it might not always be 1. If you start at 0, then you would use the 0. Whatever the first term is, we have to prove that the recurrence 1 is equal to the function 1. So P of 1 is 5, and F of 1 is 3 times 1 plus 2, which is 5. So we're good. 5 equals 5. So we're good to go there. Now I know I said 2 steps, but I'm going to kind of break that second step up into 2 pieces. I'm going to write the inductive hypothesis and then use it to prove the inductive step. So we have the inductive hypothesis. Hypothesis. And this is essentially where we say, assume that P k minus 1 equals F of k minus 1 for k is greater than 1. That's just like the generic statement that you kind of always need to have. But let's also remind ourselves what that would actually mean in terms of that function. So P of k minus 1 would then be equal to 3 k minus 1 plus 2. Now I steal these notes from someone else, but they said in their little solutions, they said go this far on WebAssign. So I assume your homework is going to want you to go all the way up to that kind of piece. And I do know that the WebAssign is kind of that obnoxious thing where they make you fill out the blanks of the proof. Those layouts are horrible. But so if you're trying to figure out what blank it wants you to go that far. So hopefully that helps. So essentially what we're going to do is we're going to be able to use this. Well, hopefully we want to be able to use this to show that this is also going to be true for P of k. So now we do the inductive step, essentially. Go away. Inductive step. How much space do I have? Am I going to run out of space? I should be able to do it. So start with P of k. Well, what would that be? That would be 3 plus P of k minus 1. Like if I just used the actual recurrence relation to write out what P of k is. Well, now I can replace that P of k minus 1 with this 3 times k minus 1 plus 2 by the inductive hypothesis. So we're going to replace this P of k minus 1 with this 3 times k minus 1 plus 2, and I'll write by inductive hypothesis so we remember. By inductive. What made me use k instead of n? K is just the variable that's used in induction. That's literally the answer. You can use whatever letter you want. If you wanted to use n, you would just have to use n minus 1 instead of k minus 1. But that variable name doesn't really matter. It's just kind of, everyone's kind of agreed that induction is always used with k. Someone raised their hand. Oh, the hand's gone now. Okay. So kind of the idea of this, maybe you don't realize what we're trying to do here, is that we want P of k to be equal to f of k. So we want this to be equal to 3k plus 2. That's kind of what we're looking for. Maybe that's not clear. So we want to try to manipulate what we have now to look like some 3k plus 2. Well, now that I've replaced that P of k minus 1, let me do some algebra. So the first thing that jumps out to me is that I could distribute, distribute it correctly, distribute that 3. Well, essentially this 3 in the front and that negative 3 that I have now because I distributed are going to cancel each other out. I'm going to get 3k plus 2, which is what I wanted. So let me just say f of k so that we remember that we made it. We did it! And kind of the last thing you say is, so by induction. Now, at the very end of this, so Sam, if you do decide to use ends, you want to be kind of careful, because now we do switch backs to ends. So the reason we start with ends and end with ends, but we didn't use ends in the induction piece is literally just convention. People just do the inductive piece with k and then just finalize it with ends. People are weird. The variable names don't really matter as long as the process is there. So that's kind of how induction goes, is that you prove that it works for the first term, you assume that it works for some generic k minus 1 term, and then you show that it works for k. Questions, concerns on that before we do another one?
So for all n greater than or equal to 1?
Yes, that says for all n greater than or equal to 1. I just kind of ran into my little side note section over here. All right, I'll leave this up for 5 more seconds. All right. So let's do another one. So this was the other one that we did the other day where we found that we guessed that the closed form was 8 times 1/2 to the n. So this was our exponential one. So base case. Does P of 1 equal f of 1? So I put a little question mark above it because I haven't shown it yet. So P of 1 equals 4. F of 1 equals 8 times 1/2 to the first. So 8 times 1/2 is 4. 4 is the same as 4. So base case is done. Inductive hypothesis. Hypothesis. So again, the inductive step, I kind of break it up in 2 spots, but so we assume P of k minus 1 equals f of k minus 1. And let me just keep going and remind myself what that would mean. That would mean 8 times 1/2 to the k minus 1. And we say this for k greater than 1. Inductive step. Start with P of k. Use the recursive definition to say what that would be equal to and try to use your inductive hypothesis. So P of k equals 1/2. So I don't know why I put a parenthesis there, but I'm going to keep it. K minus 1. Oh. Stop it. Our inductive hypothesis tells us that we can essentially replace this P of k minus 1 with this 8 times 1/2 to the k minus 1. And again, maybe a side note to remind us what we're looking for. We're essentially looking for an 8 times 1/2 to the k. Well, I've got a 1/2 k to the minus 1. I've also got a 1/2 in the front. So if I kind of rearrange this a little bit, I would have 8 times 1/2 to the first times 1/2 to the k minus 1. Since those are both 1/2, you can smush them together and add their exponents. K minus 1 plus 1 would be k. So we get 8 times 1/2 to the k, because we do k minus 1 plus 1, or 1 plus k minus 1, whatever floats your boat. Using exponent rules. So this was just to remind us that we've made it. That is f of k. So we're done! By induction! This is true for all n greater than or equal to 1. So, by induction, p of n equals f of n for all n greater than or equal to 1. Have it? Okay. Got one more full one, and then a tiny bit else, which hopefully will be.
Greater than equal to, or just greater?
So it can be greater than or equal to, because the equal to essentially comes from the base case. Because it was true for 1, and then we proved that it was true for greater than 1. So it's true for both.
Okay.
Good question, though. All right. 5 more seconds. Okay. One more full one. We did one more the other day where it was that kind of super algebraic one where we found the quadratic equation that matched. So let's do that one as well. Oh, my little thing that didn't match. Anyway. So same idea. Use induction. What's the first thing? Base case. Base case. Does P of 1 equal F of 1? P of 1 is 1. F of 1 is 3/2 minus 3, what? Minus 3/2 plus 1. The 3/2 and the minus 3/2 cancel each other out. We get 1. Base case is checked. I didn't put in my little 1 squared and times 1, but hopefully that's clear. Inductive hypothesis. I love induction, guys. Inductive hypothesis. And that's our assume that it's true for some k minus 1 for k greater than 1. So assume P of k minus 1 equals f of k minus 1. This one's going to get a little bit gross algebraically, but it's going to be all right. If I can do it with my terrible arithmetic brain, y'all can do it too. And we always say for k greater than 1. Because essentially we've shown it works for equal to 1, and now we want to show that we can take something greater than 1 and get to that next step up. Because if you think about it, if k is greater than 1, then the first thing it can be is 2, and the k minus 1 would be 1. So this does cover all steps. Anyway, inductive step. It's going to be a bit more algebraic work, but we got this. Start with the P of k. Use the recursive definition first. So we've got P k minus 1 plus 3 times k minus 3. Let's remind ourselves what we want. We want f of k, which would be 3/2 k squared minus 3/2 k plus 1. Once you have p of k, oh, I'm going to run out of space if I don't write smaller. We take our p of k minus 1 and replace it with its kind of gross thing that it is. I'll be honest, it's a little gross. So 3/2 k minus 1 all squared minus 3/2 k minus 1 plus 1. I'm going to zoom in a little bit so y'all can see the algebra that I have to now kind of squeeze in here. And I'll zoom back out in a minute. So we want to try to find some 3/2 k minus 3/2 k squared minus 3/2 k plus 1. So we probably have to FOIL and distribute all this out. So let's do it. Woohoo! So let's FOIL that first. So if we FOIL that out, we'd get k squared minus k. So if, can I do minus 2k plus 1? I'm going to do all the distributing at one time. So let me just rewrite that last piece. And then distribute. 3/2 times 2. Those 2's are essentially going to cancel out. We're just going to get minus 3k plus 3/2 minus 3/2 k minus 3/2 plus 1. Wait. No one screamed at me yet. I've forgotten this whole entire piece the entire time. What have I been doing with my life? All I've had is the p of k minus 1. I've forgotten that 3k minus 3 this entire time. So plus 3k minus 3 plus 3k minus 3 plus 3k minus 3. I'm sorry. I got a 3/2 k squared. I'm going to probably hope that that's going to stick around. And what do we need? We need plus 1. Well, I've got that floating around there, so that's good. And I've got a couple k's floating around, so we hope that those are going to stick around as well. What's going to happen here? Why is my brain not working? Yeah, okay. So what do we've got going on here? We've got a 3k and a minus 3k and a plus 3k. Those are going to cancel each other out. We've got this minus 3 over 2k that's probably going to hopefully stick around. What do we've got left? We've got a 3/2. Oh, sorry. I made another goof. I'm really sorry. When I distributed this, I was distributing a negative 3/2. It should be a plus 3/2 instead of a minus 3/2. Sorry. So we have a 3/2, and we have another 3/2, and we have this negative 3 in the back. 3 over 2 plus 3 over 2. Common denominator, so you can just add their numerators. So we get 6 over 2, which is 3. 3 minus 3 is 0. So actually all of those 3 terms, the 3/2, and the negative 3 are going to cancel each other out. So all those go away also. What am I left with? I'm left with exactly what I was hoping I'd be left with. 3/2 k squared minus 3/2 k plus 1, which is f of k. Like I said, a bit more algebraically dense on that one. But not horrendous if you just aren't like me and make small little mistakes of distributing. I'm human too. Sometimes I mess up on math. if I want to be correct here, I should do my so by induction. P of n equals f of n, for n is greater than or equal to 1. And seriously, that's how induction goes. Sometimes it's a little algebraically tricky to figure out how to get from P of k minus 1 to P of k. But you just write it out using the recursive step, replace the thing using the inductive hypothesis, do a little algebra, pray to the math gods. Hopefully it'll fall out the way you want it to. And if it doesn't seem to be falling out the way you want it to, it's probably not something you can prove by induction, or not something that's true at all. You shouldn't really encounter anything in that class because we'll be trying to prove things that are true. But in general, if it didn't seem to be working out, then maybe it's just not true. Good. Questions, concerns? Okay. Be careful when looking for patterns. Not every pattern will hold. So if we want to show that a closed form is not correct, then just like way back when in chapter 1, when we wanted to prove that something was false, we just found a counterexample. Same idea here. If you feel like it's not going to work out, you just need to find one counterexample to show it doesn't work. So, also that's the other thing that is why we have to prove this kind of thing. If you think about like this little staircase thing that I was talking about originally, with these kind of ideas in what things we prove by induction, there's pretty much usually an infinitely many amount of cases. So it's not like you can just sit down and prove that all of them work, which is why we need to do this inductive step, because you would be there until the end of the world. So do not think that just saying, oh yeah, it works for the first 5, so it's going to work for all of them is enough. You would have to prove it by induction. But say we look at this one, and we want to say, well, what if this recurrence relation is equal to the, what have I done? There we go, equal to this function. So this recurrence relation, we're guessing is going to be equal to this function here. So let's start looking at a table to see if this looks like it's going to work out. Well, what's P of 0? Well, that's the one that's given to us, that's 1. What about F of 0? Well, we'd have, can I do it really tiny down here? Probably not. We'd essentially have 2 times 2 to the negative first, which is essentially 2 divided by 2, which is 1. What about P of 1? That would essentially be 3 times 1 minus 0. No. Sorry, minus negative 1 squared. Are my notes wrong? Is my brain wrong?
Is 2 to the negative?
No, that would be 0 squared.
Is 2 to the negative 1 is 1/2?
Yes. So essentially, if you have x to the negative n, that's equivalent to 1 over x to the n. So 2 to the negative first would be 1 over 2 to the first, so 1/2. Yeah. Why is my brain not working? Why are my notes weird? Because you'd plug in 1, and then 1 minus 1 is 0. Oh, because I'm an idiot. That's why. I'm an idiot. 3 times 1 minus 0 is 3. Sorry, I'm an idiot. I'm losing my mind. What if we plug it into the other one? We would get 1 plus 2 is 3 times 2 to the 0. Anything to the 0th power is 1, so that's 3 times 1 is 3. What about P of 2? We would have 3 times 3 minus, now 2 minus 1 would give us 1 squared, so 3 times 3 is 9, minus 1 is 8. What if we plugged it into the other function? 2 plus 2 is 4, times 2 to the 2 minus 1 is 1. 4 times 2 is 8. So it looks like it's matching up pretty well so far. What about the third term? That would be 3 times 8 minus 2 squared. So 3 times 8 is 24, minus 4 is 20. And then we'd have 3 plus 2 is 5 times 2 to the 3 minus 1, so squared. So 5 times 4 is also 20. Still looking good. You can probably assume what's going to happen next. We plug in 4, we'll get 3 times 20 minus 4 minus 1 is 3, so 3 squared. So 3 times 20 is 60, minus 9 is 51. If we plug it into the function, we'd have 4 plus 2 is 6 times 2 to the 4 minus 1, which is 3. 2 cubed is 8. 6 times 8 is, I just ruined the big hoop, is 48. 48 is not equal to 51. So we found a counterexample. So if we were to just start looking at this and we just did the first 3 terms, we would probably think that that looks pretty good. If you were to try to then prove it by induction, you would probably run into some kind of weird thing where it's not going to work out. Because if you go to the next one up, you start to realize that it's not actually going to work out. Which is essentially what this hoopla here says. If we only looked at 0 through 3, we might be tempted to assume that it is correct. But that's why it's important to prove it by induction. Proof by example does not work. So just testing a few examples is not a proof, like I was just saying a little while ago.
If it doesn't work out, you just assume that it's
Well, yeah, that's the problem, right? You think that you screwed up somewhere instead of the actual thing not just working. I totally get that. All right, we should be able to finish this last little section. So, remember way back when we defined a function that kind of looked like this, but it's actually different? When we defined earlier was the bottom pieces was the little foot, and now the feet kind of on top. So the other one was called the floor. This is called the ceiling. So the ceiling function gives the least integer greater than or equal to x, where the floor was the greatest integer less than. So if I have 2.7 and I want a number that's greater than it, but the least integer that does so, that would be 3. If I start at negative 3.2, I want to go greater than it, so I want to go to the right on a number line. But the least integer that does so would be negative 3. And just like last time with the floor, if you have an integer, the least integer greater than or equal to 8 would just be 8. Now this last piece, if any of you have the thing in front of you to look at it real quick, looks terrifying, but it's going to be quick and easy because we're going to plug it into a calculator and make it do half the work for us. So remember we talked about the lovely Fibonacci sequence, the 1, 1, 2, 3, 5, 8, 13, 21, blah, 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 blah. And we gave it as a recurrence relation. That P should be an F, because then the rest of it doesn't match up. So it says P right there. Should be an F. So I want to know whether that's true, that that's equivalent to the ceiling function of e to the n minus 2 over 2. So how we're going to figure that out is we're going to have a calculator do most of the work for us. If you don't know how to use your calculator to make it do it for you, I'm going to show you how. Really super quick. So let me just do this, and then I'll pop over here. So if you have a TI 83, 84, whatever, this is how you would do that. So say you wanted to, so go back here really quick. The way we're going to look at the ceiling is we're actually going to look at the generic function first, and then just find the ceiling. Putting ceiling into the into a calculator, it can probably do it, but to be quite honest, I don't know how. What is the difference in the n minus 1s? Oh, Sam, sorry. So way back here, you asked what's the difference between the n minus 1s. notice that this one is attached to P and this one's not. So when it's attached to the P, that's actually part of like the function part. It's a function value, where that second one isn't attached to a function name at all. It's just n minus 1 all squared. So we just plug in the value there. Whereas when we have P of n minus 1, it's an actual function value. Madison, you had your hand up. Did you have a question? Maybe we won't do this one. Maybe we'll hit that on Tuesday, but that's okay. Yeah, we can probably do it really. So what we're going to do is we're going to find the values of e to the n minus 2 over 2 and have our calculator do all the work for us. So if you go into the y equals, so essentially if you hit second just regular y equals, and then you type in e to the x minus 2 because the variable name doesn't matter, put that in parentheses because it can't make it, if you don't put it in parentheses, it won't do what you think it does. And then if you didn't know this, if you hit second graph, it pulls up a nice little table for you. And since we wanted just the values from 1 to 11, we can just pull out all the numbers from 1 to 11. So I just got to scroll down to get 11 in here. And then we can just copy this sucker down here. Is there a way for me to get this to look nicer? I just want you to zoom in. Okay, I'm gonna do this one. Blink. There we go. So I just copy those down. So we've got 0. Oh man, we've got 0.60653. We've got 1.6487, 2.7183, and so on. 20.086, 33.115, 54.598, and 90.017. If we want to find the ceiling of all of those, what's the least integer greater than 0.6? That would be 1. So that one matches the Fibonacci sequence because 1 equals 1. Notice the Fibonacci sequence is in the last column of this table. It's just written out for us. Least integer greater than 1 is just 1. That matches the Fibonacci sequence. Cool. What about the next one? That would give us 2. Matches the Fibonacci sequence. Least integer greater than 2.7, 3, matches the Fibonacci sequence. 5, matches the Fibonacci sequence. Least integer greater than 7.38 would be 8, matches the Fibonacci sequence. 13, matches the Fibonacci sequence. Least integer greater than 20.086. So that 0.86 is really saving us because that bumps us up to 21, matches the Fibonacci sequence. If you were doing this by hand or just by yourself and you wasn't forcing you to go up to 11, you'd probably stop at this point and assume it's going to work. But Next one would give us 34, matches the Fibonacci sequence. 55 matches the Fibonacci sequence. But all of a sudden, once we get all the way down to the 11th term, we've got that the ceiling's going to give us 91, which is not 89. I know, shocker. 91 is not equal to 89. So essentially what we've shown now is that we've found a counterexample to showing that the Fibonacci sequence is equivalent to this ceiling of e to the n minus 2 over 2. So let me just, for clarity's sake, So no, because it was asked, is it true? Since the ceiling of e to the 11 minus 2 over 2 is not equal to the 11th term of the Fibonacci sequence. So in general, the Fibonacci sequence cannot be equal to that ceiling function. So semi-cool example. Well, maybe I'm weird for thinking that. Also a reminder of how wonderful the table function is on your calculator. And a reminder that we just need one example to show that something is not true. So that's done 3-2. I believe what that means is going to happen for your exam is we're going to cover 3-3 on Tuesday. I honestly don't think it'll take all class because it's a somewhat shorter section. So hopefully we'll have some time at the end to go over any review questions you guys want to go over. But that'll be your exam. It'll go up to 3-3. So I think, was there any chapter? No, there was some chapter 2 material in your first exam. So we're starting somewhere in chapter 2. Once that review sheet is up on Blackboard, that'll tell you exactly what sections to look up.